In this video, I will show you how to use differentiation to find a function's local extremas in a concrete numerical example. But not to find these points, but also to decide whether these are local maximas or local minimas with the usage of the second derivative. So let's jump into it. Let's consider this f of x function, which visualization can be seen here in the coordinate system. And so we are dealing with the derivatives. And as you can see, there are some local extremas of the function. And what we can notice is that the derivatives at these points are zeros. So if we drew here the tangent line at these local extremas, then we would be able to notice that these are horizontal lines, so which means that the derivatives at these points are zero. But not only these points give us zero as a derivative, because, for example, as you can see here, we also have a zero derivative, and also here at this other point. So there are, in this case, 5 places where our derivatives are zeros. So here we can write that in all these examples that the first derivative is zero, which means that we might have a local extrema, local maxima, or local minima at these points. But how can we investigate whether these are really local extremas? This we can investigate by looking at the second derivative at these points. So if we look at this place at, let's say, x1, okay, let it be then x0, this is x2, and so on. So this is x3, and this is x4. So at the local maximas, we can see that the second derivative, which show us how the first derivative changes, is negative at this point, because here, as you can see, the first derivative is decreasing. Here it reaches zero because, as I mentioned, this tangent line is horizontal at this point, and after that it decreases further. So the second derivative is negative. And also this is true for the x3 point as well. So it is negative here. What do we have at local minimas? So as you can see, the second derivative here, it is increasing, because here we had some negative value, and then as the function goes on, it reaches zero, and after that it will be positive. So the second derivative must be positive at these points. And there are two other cases, x0 and x4, when the second derivatives are not negative and not positive, but these are zero at these places. So the second derivative at these points are zero here as well. And these are the inflection points. So, and here as well. So here we had local maxima. Here we had local minima. So let's summarize our derivatives and second derivative at local maxima, local minima, and at the inflection point. So here we have this table where we will summarize the properties of the second and first derivatives. We saw that all the derivatives were zeros at the points, but the second derivative were different, and namely at the inflection point we had 0, and the local minima, the second derivative was positive, and so let me write here a plus sign, and at the local maxima the second derivative was negative. So this is the basically the most important rule that you have to remember, and this will be enough for our purposes when we solve math or physics problems, mostly with one single variable. And let's just solve a concrete numerical example where we have g of x, and this is 4x to the power of 3 minus x squared plus 10. So here we have this function, and we would like to find all the local extremas for this function. So first we should calculate the first derivative of the function. The derivative we can calculate with the numerical approximations with epsilon, but if you know the derivative rules, then you can also use that. So the derivative will be here 12x squared minus 2x. And so we are looking for the local extremas. This is why our derivative should be equal to 0, which means that 12x squared minus 2x's are 0. So the common we have here is 2x's, so here we have in parentheses 6x minus 1, and this equals to 0. And this means that the first solution is equal to 0, and x2 is, so here in the second term, it should be equal to 0, which means x2 is 1 over 6. So in these places, the first derivative is 0. But how do we know that at these places we have local maxima or minima? And in this, the second derivative helps us. If we differentiate the first derivative again, then we will have the second derivative, but sorry, not with f, but with g. So g double prime of x is 24 times x minus 2. And we should check whether these values and these places are positive or negative. So at 0 we have negative 2, and at 1 over 6 we have 24 times 1 over 6 minus 2, which is this is 4, I think, minus 2, which is 2. So this is positive and this is negative, which means that at 0 we have local maxima, and at 1 over 6 we have local minima. So in this video, what you should remember is that table in the middle of the video, what I wrote there, because we collected there the first and second derivatives, and we summarized how to find and categorize the local extremas of a function. I hope I was clear, and we will meet in the next video.